All right, so today we're going to get into understanding color, how we see color, how we don't see color, how important it is to use color, and then the next lecture will be color plus other techniques for displaying 2D scalar fields. And then that kind of will build the rest of our visualizations on those. Again, as usual, our opening will be seeing some examples.
Speaking of contrast.
Yeah, this is like the worst color, blue
Fail.
and blue. Yep.
You should take a visualization class.
I know. It used to be black on blue, which is still pretty bad, which we'll find out later today.
Have you noticed that books are always white pages with black text?
I made it white pages with black text, and then the students thought it was poking their eyes out. It was too much. So now it's blue background. All right. So this is looking at a combination of an image analysis and visualization tool. It's actually visualization in support of image analysis. And so what they want to do is segment these neurons that are going through this slab of 3D volumetric data. And so one step is kind of setting the transfer functions, and we'll talk about transfer functions on the visualization lecture on 3D, so that they can kind of highlight the areas that they want to see, and then kind of semi-automatically start labeling things and have them, the regions grown kind of down into the surface. And so there's most the kind of the 3D data for the context, and then they've got the 2D geometry that are the segmentations that come out at the end, and they want to compare them against each other and see how well the segmentation algorithms are doing. So here we've got a nominal coding of different named neurons, and they're comparing them against the volume data. And so the first thing they can do is just kind of trade off spatially slicing. This part shows the volume data, and nothing behind it. This part shows the kind of segmentation data. But they're also going to be able to enhance these ridges with pre-filtering to give some kind of a region of interest, and so you can see kind of the areas that you want to do. Right. So they're running an edge detector. Median filter is your friend for lots of medical images. The median filter has the disadvantage that it kind of puts stair-steppy things in your data, so you median filter and then a little bit of a Gaussian filter, and you get a smooth thing with the giant bright things and dark things turned out. Here they're adjusting the opacity based on the intensity of the gradient magnitude, right? And so this is kind of showing you, highlighting the edges where you probably are going to want to segment things, and hiding the other parts to start giving you an idea of where you would want to place these things. All right, and so now I think they're going to talk about how they accelerate the rendering structure, which is not so relevant to our question of how do you pick a technique, but rather how you would implement the techniques. So this is a visualization of the Millennium Run, which is a simulation of the entire universe from the beginning of time until, I don't know if it's now or sometime in the not recent past. And so this is basically how do we render all these kind of glowing gas things that are around in space. And so this is a volume rendering technique that kind of splats things and adds the color from back to front, but also things in front can include a little bit the things behind, right? And so this is trying to really simulate what you would see as light comes through these star clusters. So each of these is kind of glowing spot with a disk around it. It's a Gaussian that a little bit includes the things behind, but mostly adds from the back to the front. You can pseudo-color by the temperature of the things emitting the light. You could actually color by that, and it would be the black body radiation spectrum, but everything would pretty much look white in that case.
So what insights do we draw from this visualization?
Yeah, the interesting thing is, this is what our collaborators at Michigan State looked at all the time. They're like, wow, it's really beautiful, but where's the high, iron elements? Where are the areas that we care about? So this was not an effective visualization for them to understand what was going on, right? So it doesn't have strong occlusion, so you don't get good front and back effects. And so this is, what they think about when we say we're going to do visualization. They say, oh, pretty pictures, but not necessarily useful for understanding what we're doing, which is why, our techniques were a lot uglier in the sense of kind of visual beauty, but they told them more information about what was going on. And I'll give an example of that, I think, later in the class. So good call. It's very pretty, but how is this, what question does this help answer, right? This kind of helps say, oh, it's a beautiful thing, I love this simulation, but in terms of answering specific questions, it may not be optimized well for that. Good.
NVIDIA is thrilled.
All right, so this is aimed at answering a specific question, which is what happens as a dragonfly flies? Right, and so the first step that they did was actually to put little markers on the wings of a dragonfly and track the dragonfly wings over time with a camera to get a 3D estimate over time of how the things move, and then they made a model of the dragonfly that they could then run simulations of airflow around to try to understand how those wings would impact the airflow. Here's an interesting viewpoint, right? This is kind of a very simplified wing with a simplified motion to get an understanding of how it sheds vortices, and this is saying, okay, well, it's actually the actual geometry wings, and kind of see how with particles air gets moved around, and to get an idea of why, where's their lift. Here's kind of a shed off the front of the wing visualization, right? This is how forwards and backwards in time flows happen there. Now we're locked in the point of view of one of the wings, right? And so this is like saying, how did you want to map your data? Well, I want to see it from the wing's point of view. The dragonfly moves around, the air moves around, but this one wing is kind of rotating and flapping, but we're keeping looking down the axis of the wing to understand what's going on. Here we've got red vortices being shed from the front wing, green ones from the back wing to see how they compare with each other. So here nominal coding is used to show how these vortices now overlap.
This is a vector field?
This is a vector field, and these are kind of particles that are vectored along the flow lines to get an understanding of kind of how...
It's like a sampling of what the individual air particles might be doing.
Yep, so
Yeah.
one particle started here, kind of went forwards and backwards, right? One started here, went forwards and backwards, and it shows you kind of the trajectory of these little segments of the trajectories, seeded randomly along kind of the front of the wing.
Oh, so the length gives you an idea of the velocity?
Length gives you an idea of the speed, yep, velocity magnitude, exactly. All right.
I guess that was a very intuitive picture then.
Yeah. So administrative. So homework, I'm going to post by next Thursday. I want to always post the homework a week ahead of when it's due. In past courses, I've missed that deadline and we just skip a homework. I'm hoping not to miss that this time. I've got all 5 data sets identified. I'm starting to get them in hand, and I'm going to get back with you scientists soon with an email describing what I think you told me, so we can have one more round of that before we post it to the first homeworks. All right. So question, from reading Colin Ware's book, how important is color? By color here, I mean hue. So it's a 2-answer forced choice question for y'all. You can either say color is irrelevant or color is critical, right? So how many people think color is irrelevant, hue is irrelevant?
Having color at all, or the specific choice of color?
Having hue at all. Yep, all right. Uh-huh, a couple people. So how many people think color is critical? 5. So it's a room full of academics. I refuse to answer a question that's a 2-answer forced choice. All right. So those of you who thought it was irrelevant, why did you say that?
Because it's said in the book that 99% of the time we can do away with color and do with grayscale.
Right. This is why black and white television works. You probably have never seen black and white television.
It's the reason
We used to have black and white television, and it
it's the reason that sodium vapor lamps work, where you have an entire parking lot in one wavelength of light, literally.
Yep.
And you will still see color even though it's not there.
Yep. So
Because
seeing
your-
shape, you
Your
don't.
brain will invent the color, and I think most of the processing hardware in our, or wetware in our brains is devoted to things that are really in the contrast domain, not in the color domain.
Yep. Yep, and so, right, so we learned from looking at this that colors are relevant to determine object shape, right? You don't see that from hue. To determine layouts of objects in space, right? How objects are moving is not, using the hue information. And, you can have laboratory assistants or other people walking around. 10% of the male population is colorblind, and color channels, they might not even know it, right? And so if you can go to be 21 years old and not know that you're colorblind, how important could it be to what's going on? So in a large set of things, it's relevant. So those of you who thought it was critical, why did you think that?
It gives you extra axes of representation. So if you're trying to fit, several things on the same visualization, then color is really helpful for that, because you could use color for an extra dimension that you couldn't have than just a grayscale image.
So it's critical because it gives us other display channels that we can show data in. Yeah. In everyday life. Right, so it's critical to kind of breaking camouflage, to understanding, you know, what is the thing, are these berries, are these leaves, to seeing, you know, what's going on here.
Are those actually the same image?
These are the same image, yeah.
No, they're not.
So the one on the right is the same image.
Oh, okay, it's not the same as the one on the left.
Right.
Okay.
So, you know, is this object, is this food ripe or is it rotten? Are these mushrooms the safe mushrooms or the mushrooms that are going to kill me when I eat them, right? What kind of stone is this? Is it going to be the kind that I hope will hold up under that?
It's not just observation, but maybe emotional aspect. Like when you're looking at red, it will tell you something more than just looking at gray. So it's some kind of emotional or
Good.
danger.
There's the whole world of art that I'm completely ignoring in this discussion, right? I'm like using how can we use color to do something useful today for us? And you're saying, look, there's a whole other world out there of art, right? And in fact, there's a course being taught this semester in the art school on visualization of science, and they're going to understand that a lot better, right? They're saying how to use the scientific data, present things in a way that gives you not just the information, but gives you an impact about why this is an exciting bit of science or why this is something you should deal with. So you're right, there's a whole other issue that I'm completely untrained to tell you about that is going on here. That's true. All right. So uses of color. So now that we've kind of, you know, thrown out the kind of two ditches, so it's good for labeling and categorizing. So indeed, if you have a bunch of objects and you wanted to group them together, you could say, okay, these are classifications of bad ones and good ones. It can mimic reality, can draw attention, and show grouping. So it's not good for displaying shape, detail, or space. You want to use luminance for that because that's how we see that. So let's go through that in a little bit more detail. So here's an example, and kind of all of the molecular examples are color showing, you know, atom type. And so here, there's one kind of color that's the blue that's used as the background that's showing the receptor site that this ligand is kind of bound into. Then there's the color that is the kind of atom type, and then a different color for the bonds, showing the kind of individual atoms that are in the ligand that's bound in there, to understand how it relates to the background. So the color is identifying which kind of atoms there are. Now here, we're seeing both hue difference and luminance difference to see that, and so even if you're colorblind, you can start to see the differences here as well. You can use it to mimic reality, right? So here are the different, you know, parts of the fish. There's the bone that's white, there's the flesh that's pink, and there's the kind of liver and the different digestive systems that are, to give you an idea, okay, this matches what I see in reality, so now I know what I'm looking at. You can use the same kind of data set with different color mapping to draw attention, right? And so this is saying, okay, here's where the toxins are accumulating in the fish, and so I want to kind of draw the user's viewpoint to the places where the toxins are high, because that's going to be the part maybe you didn't want to eat, or maybe you understand the impact it had on the organism. As you mentioned, showing grouping. So here is the same, you know, kind of multi-dimensional data set. It's a 2D plot of plots on the left, where there's kind of, you know, axis 1 versus axis 2, axis 1 versus axis 3. So all of the projections are shown over there, but the dots that are in a projection are kind of ambiguous. Which ones match up between projections, not so easy to see. Whereas on the right, you can then color by one of the different axes and get more display in the same data set. Right? So here's not only the way they lay out in space in these 2 dimensions, but here's a 3rd dimension, how they spread and how they cluster in the display.
There's used very few colors, though.
Yeah, it turns out that there's very few colors that you can do with this one.
It's got like the primaries and the complementaries, and that's it. Right?
Yep, and it turns out that if you try to do more than about 6, there aren't any. Yeah, I mean, you can't tell them. We're going to get to that in just a little bit. All right. So if you wanted to understand data sets and the details of them, you don't want to use only hue, right? So luminance variation is required for detail. So the little not happy face guy, he showed up in like the 3rd year I taught the class because I would show these slides, and the students would say afterwards, well, you showed a bunch of slides, some were good, some were bad. Which ones do we do, right? And so this should then label what is the bad thing, because it's some case that there's, you know, the picture is just completely bad, but sometimes there's only one aspect that's bad. So I tried to describe what it is that's poor with this particular image. All right. So here there's not a luminous contrast across the middle, and so you don't see detail much in this display. Okay. All right. And so let's look now a little bit at color models. How do you represent color? And how you represent it depends a little bit on what you're trying to do, right? If you're a hardware manufacturer and you're trying to represent colors on a display device, your space may be red, green, and blue, or if you're doing a printing process, it will be cyan, magenta, yellow, and black, and so it's kind of this attractive color space. There's intuitive color spaces that are kind of described based on familiar terms, hue, saturation, value, and we're going to see some of those. And then there's the attempt to make perceptually uniform color spaces, right? So that we don't have these large green areas and then sudden changes. How can we make a uniform color map? And there's kind of just examples of those, and we'll go through those each. So here's the red, green, blue RGB color space, and so the back corner of this cube is black and the front corner is white. There's a red axis, a green axis, and a blue axis, and then the three other corners are kind of the sums of those two colors. And so you can think of it gets brighter as you go from the far back to the near, and this is what we think of in computer graphics. This is typically you simulate the amount of red light, green light, and blue light reflecting off surfaces and finally coming out of the screen. You can also remap this space to think about it for hue, saturation, and value, and this is a kind of a more intuitive space. So again, the intensity goes from black at the bottom to top at the right, so that's the value. Or if it's hue, lightness, saturation, that's the lightness. And then there's several different spaces that are basically the same. Then there's the color wheel around the outside, right, which is the hue. And then there's the saturation, which is less saturated in the middle and more saturated near the edges. So less saturated is more mixed with gray, so that right at the middle is a gray axis. The most saturated is in the middle. And you can see that as you get brighter or darker, your kind of maximum saturation gets less, right? And so you can't get as far from the unsaturated axis, because like if you're at white, all your kind of your red, green, and blue are at full, and there's nowhere to go away from that. If you're as bright as you can be, you can't get very bright and saturated. So this is kind of the gamut of a display space. You could, of course, have brighter saturated things in the real world if you just had shining through the sun and had a filter coming out the other side. So there's been attempts made to basically make color chips, lay them out on a table, and ask people to say, okay, show me which color of the two chips are as different as these two color chips, right, to try to unify the differences. And so you get kind of a very sudden change across the green, because we can't see subtle changes in green, and then slower changes across boundaries, and then layout of space. And so there's a CAIE lab is one of these spaces, and there's LUV space is another one. And so you can basically, if you're trying to do colors that are in the same family, but equally distinguishable, you can use these spaces. And there's kind of available, I don't know if there's online on web pages, but certainly code for transforming things from one color space to another. And so if you go in ParaView, for example, you can actually choose, do you want to be specifying your colors in an RGB space or in HSV space, right? And so it'll interpolate the colors differently, and you'll get a different path through color space as you...
Do those two have the same gamut?
Well, the monitor itself has the same gamut, and so...
Well, right,
yeah.
but the color space may have maybe a subset of the monitor, right?
That's right.
So, or on another display device it may be different. So I mean, that's one of the things you go, even in video formats, you can sometimes all this stuff, but you wind up with trouble where you have colors that just don't map in, right?
Yeah.
So,
Right.
is this equivalent to YUV, the L being Y?
Say again?
There's YUV in video, right? So is the L the same?
So YUV in video is different. Y in that case is brightness, and then U and V are two different color axes, the blue,
Yeah.
yellow, and the red, green. And so that's different than this kind of perceptually uniform space, but you can map between them. All right. So opponent process theory. And so it turns out that you do have red, green, and blue cones in your eye, and they're kind of the first thing that fire, but very early on, the signals get kind of combined. And so what you get is a red plus green signal that forms luminance. And so that's kind of the up-down channel, although it shouldn't really be black to white, it should be kind of black to yellow. And then there's a subtraction of red and green, it's another signal that's kind of this axis, and there's a subtraction of luminance and blue, which gives you this third axis, all right? So this is another reason not to use blue to indicate shapes of colors, because blue actually doesn't contribute to the luminance calculation, which is used in shape, right? So now if you look at a blue on a monitor, like this kind of faded blue in the background, that's actually a mixture of not saturated blue with the other colors. And so you will kind of get some shape from that. But true blue, if you have a blue LED or a black light, you know, you look around and seeing the shape of the thing is really hard to do, right? Because that's not part of what your brain normally uses for computing shape.
Huh.
It's odd. Yeah, this is one of the things your brain doesn't do the way you thought it did.
Are there any theories as to why? I'm
Wow.
just curious.
Why are we made the way we are? There's a lot of theories about that. Right, so this is actually, if you go, you could buy, it sounded weird, they would talk about these yellow colored, you know, sunglasses you could get, and they would say it would sharpen your vision. And you're thinking, no, that's ridiculous, it can't sharpen your vision. Well, it turns out it does. It blocks out the blue, which you didn't use for luminance shape anyway, and the blue is focused at a different place, and so it made everything fuzzy. So it actually does sharpen your vision by removing the blue that you weren't actually using to see shape anyway, and so, yeah. Science plus marketing yields a product that sounds ridiculous, but nonetheless works.
The other thing is that the response curves for green and blue are much further apart than red and green, right?
Yep. And
So
we're gonna
red
see
and
that.
green almost overlap, and then green and blue are further apart, so.
Yep.
Yeah, as we evolved, red is sort of a later addition, I think. Lower animals have red and blue.
There's one theory. Chickens
Probably a
have,
biologist in here. that's gonna
chickens
beat me
have
to that,
7,
but-
so yeah.
They have 7? Really?
Yep. All right.
I didn't know.
How
No,
do
well, it's good.
I know because somebody dissected a chicken eye.
I knew you were talking to the chickens.
So don't try to hide a tank from a chicken because they're going to see it, right? And so this is a kind of the fundamental space. Go ahead.
I think I just remember something. I think the reason we don't use blue because in nature there are very few blue things.
Uh-huh. Blue is not something that shows up a lot. So water,
Yeah.
sky, and it's usually in the background, and so good
It's either
for
the sky or water.
Yes.
Food and enemies or predators are not colored blue.
Right.
Yeah.
It's just the bluebirds that they get the hide out from us. All right. So this kind of forms a three-dimensional space. When you think about it, this is how we think about color, right? We don't talk about a greenish red, right? And so as you kind of name these things, there's no greenish red, there's no yellowish blue, right? Because that's not in our fundamental way of thinking. Those are opposite ends of the same spectrum. Across cultures, if you look at the appearance of color names, if there's only 2 names in the language, they're black and white, right? So it's kind of the luminance channel. If there is 3, then red is the next one, right? You can imagine why. Blood would be an important thing to talk about. 4th and 5th are yellow or green in whatever order, and then 6th comes blue, right? And so the first 6 colors you get are these kind of opposite ends of the kind of mapping. So this supports the component color theory, but also does, you know, dissecting things and seeing how they behave. Next comes brown, and then pink, purple, orange, and gray, right? And so these are kind of the colors that people talk about as distinct.
And brown is, I always found brown weird because brown is not, there's no brown in the rainbow. It's one of
Yeah.
those weird things that,
You're gonna love the last slide.
really? Okay.
Yep. There is no brown.
Pink is another weird one.
Brown only
Yeah.
shows up as dark, so brown is the same thing as dark yellow. There's no way if you have somebody in a room and you just show them a point of light that they'll ever call it brown. It'll always be yellow. It has to be a yellow that's darker than the things around it, and then it's,
So brown is yellow.
but it's special. It's not, but people don't call it dark yellow, right? So if you put brown in there, you might think, oh, that's just dark yellow, but no, people will call it brown. So brown is a special
Are you going to talk about pink as well?
color. Pink, I'm not gonna talk about pink.
Okay. We'll talk about
All right, so color categories. If you give people a set of dots, each of these dots is slightly different from each other, and you ask them, what color is this dot, right? This is the 75% area, right? So this says that within this area, 75% of the time, people call the color pink, right? And so here's one of the pinks that was in this area, just an example. White, there was only 75%, only this was the spot where they ever called it white, right? Green, there's this area here. Aqua, that's the only aqua, right? So people were really, sure about aqua. Yellow is smaller, orange here. Blue is this giant range here, and purple, right? Right, so this is kind of, exposing some of the reasons for this non-uniformity in the color map is there's a lot more colors that people would call green or pink than there are colors that they would call aqua or yellow or orange. And so the yellow is shorter, the orange is shorter, the red, but then there's this giant green, and the blue is very kind of stretched out.
And no pink at all.
Nobody calls anything in here pink, yeah.
It's not, there is no color pink.
Are you going to tell me that pink is like brown?
No, pink is, if I remember the explanation correctly, pink is it's an illusion that your brain fills in for something you actually can't, for a wavelength you can't see.
I don't believe
I
that.
have to look that up, but
Uh-huh.
something to that effect.
I would call it unsaturated red. I'm pretty sure about that, but we can have a discussion, or look up somebody who's looked at this. All right. So only 8 hues were consistently named across this whole thing. So if you look in your kind of Crayola, color chart, you've got a whole bunch of other ones. If you go to the store, they got a bunch of other names because they have to name them something. But these are kind of fundamentally how many you have. This is why you only have 6 or 8 colors in any kind of display, because that's about it. All right. So this says that there's only a few colors available for labeling, not 210 that we see here, but only like the 8 that we see labeled. All right. So if you look at hue versus luminance in terms of sensitivity, we're going to start to see why luminance is used for kind of shape detection. So the spatial sensitivity, the red, green, and blue-yellow channel each have about a third the detail of black and white, right? So if you have a complete change from yellow to blue, you can see features that are only 3 times as large as the features you can see when the complete change from black to white. Stereoscopic depth, right? And so if you try to see what stereo is going on, if you do it in luminance, people can see that. So you've even seen these random dot stereograms, perhaps. They're basically 2 kind of images. They're 2 noise patterns that have a correlation, so you can fuse and see some things up close, some things far behind. Sometimes they add color to those, but if all you had was one of those based on hue, you could never fuse it into depth, right? But if it's only based on luminance, then you can fuse it into depth. And so our understanding of matching of things in space to see their depth has to do with luminance. Temporal sensitivity. So moving patterns that have hue-only differences, I'm going to show a video of this, look slower than moving patterns with kind of luminous color differences, right? And so, and this is a case of, we're going to talk later about the receptors in your visual system where there's actually motion detectors that kind of fire when there's motion, and so they don't respond as strongly to motion that's happening because of hue changing. So shape from shading, in other words, what is the shape of this object, works well from luminance, but not shape from hue, right? And I forgot to bring the magazine where they kind of colored all of us in rainbow color, and you can't tell what is going on. All right, for category though, hue is going to show up more answers than luminance, and so we're going to find out later you can only do about 4 levels reliably of brightness because of contrast surround effects, whereas hue you can get 8 of them, and so it's going to be better for labeling. All right, so color spatial sensitivity, right? So it's very difficult to read text that is the same luminance as its background, right? If clear text is to be presented, you have to have substantial luminance contrast with the background color. It's particularly difficult if it's in the blue-yellow direction, right? So there's somewhere in the middle, it's going to be hard for you to read what that text is, and that has to do with this particular display's gamut where they're isoluminant. And so one of my favorite quotes is, "The only exception to the requirement for luminance contrast is when the purpose is artistic effect and not clarity," right? And so for the purposes of visualization, I'll be wanting clarity. For purposes of art, there's actually good reasons to use isoluminant things because they seem to shimmer and have very interesting visual effects. All right, so here's an example of color temporal sensitivity. Yes, please. All right, so this is going to be a pattern which has an object moving back and forth against a background, right? And if there's luminous contrast between the squares, you can easily see the shape of the foreground object and the same of the background object. But when there's not luminous contrast, you can tell that there's things moving, but it doesn't pop out, right? And so what I see when I look at this right now is it's really hard to tell what's going on. At other times when there's more contrast, I see a very clear rectangle that's kind of moving counter to the background, right? And so when the luminance is the same, it's like there's something going on, maybe somewhere. If I kind of look very carefully at a spot, I can tell that there's something going on, but the percept of an object just goes away, right? And as the contrast increases again, and I start to see the shape again, and I can get a figure surround background happening, right? So this is not stereo. We're not seeing a stereo display here, but we're just seeing the shape of the boundaries kind of come out because there's luminous contrast. It comes into play and not into play. Anybody not see that? Great. All right, so this one works about half the time for a given projector in a given classroom. So we're going to see how this goes. So this case, we're looking at a high luminous contrast set of spokes in the middle that are going to spin around, and a low luminous contrast set of things spinning around the outside, all right? So your job is to look right there in the middle and let your brain tell you how fast these things are spinning, and what happens, for some distances and correct my monitors, is the outside seems to move more slowly than the inside, right? But then if you go and look at the outside, you can see, no, that spoke is staying right along with the outside one, but in the middle, you can see the kind of higher contrast motion moving at regular speed. And so this one isn't as compelling always as the other one, but sometimes works. All right. So if you look at the question of color for labeling, then again, it's comparatively effective for nominal coding, right? So if I just want to show different names of continents or different names of political parties or so forth, you can only get about 4 gray values. We'll talk about an experiment that Colin Ware did on that subject to see what we can see that. And so this basically, the other effect is now you have luminance free to show shape, right? So if you want to kind of color regions of the globe or regions of mountains, you can use the hue to indicate regions, but the luminous contrast to see the shape, and you kind of get both benefits in the same image. So it's like you said, you can add on some more layers of information. So you need to consider the kind of how many unique hues there are, right? And so Chris Healy did his dissertation topic on this, and found out that if you could go all over the luminous gamut, you get a lot more, but otherwise you're down around 6 or so distinct hues. There's contrast with the background, deal with color blindness, so 10% of the male population and 1% of the female is red-green colorblind, and so if you use red and green, they can't tell the difference between that. There's kind of how big the spot is going to be, and we're going to see an example of that, and then conventions. And so we're going to go through several of these. All right, so the distinctness is one question, and there's kind of 2 levels of distinctness. One is what you can see rapidly and without paying attention, and there's what you can see if you very carefully look around, right? And so here what we've got is basically looking at 4 different colors and a color that's in between them inside their gamut, right? So if you look for the gray dot in the field of dots here, you basically have to look all around until you can find it. Whereas here, the red dot is outside the convex hull of the other colors, and so if you look over here, you can just see the red dot kind of independent of the other number of dots there, right? And so sometimes you're wondering, well, how come sometimes I can and sometimes I can't? The answer is if you look outside the convex hull of those colors, then you can see it rapidly, but if you have something inside the convex hull, you can't. Right? Chris Healy again looked at the question of how many unique hues could you find if it was isoluminant versus not. There's somewhere between 5 and 10 that you can use. So basically, Colin Ware lists out for us here, okay, there's the red, the green, the yellow, the blue, the black and white, the pink and the cyan, the brown and the purple, the orange and the let's see, a gray. All right, and so this is one time in the class when you can just know the answer, right? A lot of times it's going to be, well, I can trade this off for this. If the question is, how do you kind of use, what colors you want to use to show nominal display of data sets, you just use Colin Ware's 12 colors, right? And here's the 12 colors that we use to do that. So here's the same colors against a white background and against a dark background. And so one thing you can see is that it's useful to put a contrasting color boundary around a region so you can see the region, right? So otherwise you would not see the white region here, you'd not see the dark region over there. And that is kind of the contrasted background, right? So you're going to kind of make sure you can kind of show your regions around there. Okay, and so then we're kind of limited to about 12 colors. You probably wanted one for the background, you probably wanted one for your labels, and so now you're down to about 10 colors that you can use if you wanted to show individual things, which matches well with what Chris Healy found in his dissertation. All right, so color blindness. Most of color blindness is red and green, and they have these tests that show you, can you kind of read what is the number there, and if you say 74, then you probably have 3 colors in your vision, and if you say 21, then you probably have 2 colors in your vision, and surprise, if you didn't know that before looking at the test.
Huh.
It turns out that there's actually two different colors of green receptors, right? And so some females actually are quadrichromats, very small percentage, and so they can tell the difference between turquoise and cyan, right? Because they have two sensors that they can subtract those forms. So if you have somebody have an argument about what color that is, it may be because it's not the same color to you, because your sensor happens to be a little bit below, their sensor happens to be a little bit above, and so indeed it looks like a different color in the color space.
What is the 74?
It's supposed to be 74,
Okay.
not supposed to be
I see
21.
71.
Yeah, so you're halfway, I guess, yeah.
Until you said the 4, and then I could see it. Because I could see the colors, but it
Uh-huh.
doesn't
It's
form a shape.
right, it's intentionally hard
It
to
doesn't form a shape.
tell. Yep, all right. So other issues, field size. You want to avoid small spots, especially in the yellow-blue direction, because you can't see the color of a very small spot very clearly. Small areas, you want to have strong, highly saturated colors so you can understand what's going on there better. Large areas, you want low saturation with slight differences, right? And you can see that the map makers have come up with this kind of on their own, not by studying perceptual ecology, but you have large areas that tend to be kind of very diffuse, and then the bright ones. All right, conventions. In the US, red is danger, green is life. In some parts of China, I'm told, red is life and green or white is death. And so this is a problem if you think your scale is going to be kind of red around the world all the same way. Some scientific domains have color conventions, and you should either kind of use them or explicitly know when you're not and tell them that you're not, and here's the reason that you're not using them. All right. So let's look at kind of features of color spaces, of color maps that we could use. And so Trumbo has got 4 different principles. 2 of them are univariate principles. One is ordered, and the other is separation. So these are 2 useful features to have for color maps. So order means you look at it and you know which end is high and which end is low, or at least which are at the opposite ends, without having to do some thinking about it. The other is separation. You can see different levels distinctly.
So perceptually ordered, do you mean rainbow?
So rainbow is not perceptually ordered. Rainbow is kind of mnemonically ordered, Rory G. Biv, right? If you happen to have in your learning that they show up in that color in the rainbow spectrum, then yes.
Have you shown us the perceptual ordered?
We're going to show you some
You
perception.
haven't shown it yet.
Yeah,
that's why I-
all right. So here's one that's perceptually ordered and double-ended, right? And so the ordering here is kind of, it gets more dark, more saturated, and that's one end, and it gets less saturated, and that's the other end. This is a double-ended scale. It's got a blue one that does that for the ocean, and then it's got kind of an orange one that does that for the land. So the oceans get deeper, the lands get taller. All right, so this is an ordered color map. And so you can kind of easily see where the land is, where the ocean is, which parts are higher, which parts are lower, right? So this is the same data shown using a not perceptually ordered color map, right? Okay, and so here, what's the land and what's the sea involves hunting around to see what's going on. It's got another problem in that this kind of reddish color here is in both ends, right? So if you look at an area, you can't tell which of those 2 it is, right? And so this has got so this is an example of not perceptually ordered color map. It's kind of got part of the rainbow down here, and then it's got some kind of a saturation section up here. And this part by itself is really not even perceptually ordered because it kind of gets brighter, darker, and then maybe a little brighter again, and the color goes off around again. All right?
I am seeing details in the, like the area on the lower, sort of lower middle left.
Yep.
In those speckles of the 2 shades of blue-green.
Yep. So this
that
has
are
got
invisible in the previous image.
this has got more separation in some places, right? Here's lots of separation. Here's lots of separation than this one did. And so if the question was, do I want to see this boundary very carefully and very clearly that's in the middle, then this might have been a better choice. If the question was, do I want to quickly see where the high areas and low areas are, this one is a better choice. All right. So this one is ordered. It doesn't have a huge amount of separation. This one is separated sometimes, and it's not ordered. All right. So this is, again, not ordered. So red at both ends, a particularly bad instance of the rainbow color map where they've wrapped all the way around the color wheel, right, to the beginning. And again, to know which color, if you kind of put these colors down in front of somebody, ask them what order they go in, sometimes they'll put them in alphabetical order. Sometimes they'll, if they're a physicist, put them in the, the kind of rainbow order. Sometimes they'll do them brightest to darkest, right? There's no kind of, you have to think about what the ordering is, not just kind of perceptually understand what's going on. So this is ordered in the sense that, at least there is an order. It's not perceptually ordered, but it is ordered. But there's choppy separation, right? So there's a sudden transition, and then large areas of the same. And not much luminous contrast along the middle. Okay. So this, is it ordered? If you know the rainbow color, if you know the rainbow ordering, it is ordered. You don't know if it's kind of low to high here or low to high here. That's okay. And so what if we do this? So this is now ordered. It's a grayscale color map, right? So it goes from dark to light. And so now you know perceptually, you would say this is high, and this is low. Is there good separation?
Not so much.
You lose a little bit of the detail in the bottom right.
That's what I was gonna say, yeah. There was a red bit over on the right that is now invisible.
Yeah. And so you can see that there's a change here, but there's quite a dramatic change. If you ask kind of how much the thing varies along here, there's a couple problems. One is that you have a hard time perceiving luminance independent of its surroundings. But the second is there's these weird kind of star-shaped things in there. So who knows what those weird star-shaped things are?
Artifact.
They're artifacts, yeah. And so this is basically, what's happening is that these are linear interpolations of these data values. And what happens then is you've got a smooth gradient, and then the slope of the color changes sharply, and you see basically your visual system responds to that by showing you kind of a star thing happening. Right? There's a very strong discontinuity in the slope, and you see that as kind of an increased brightness.
Why didn't that happen with the other?
Why didn't that happen with the other one? Because we couldn't really see much.
It
Right? So you get a zigzag thing here, right?
She's not as prominent.
Which is not as prominent. And it's also harder to see because there's no luminous contrast there. So you're right. So the features were there, you just didn't notice them, right? And so
Are there actually, in the data, are there actually ISO somethings in those diamonds, or is that a
so we're looking at basically the grid. And so here's one data point, here's another data point, here's another here's another data point.
So it literally is aliasing, it's a Nyquist
It's an
artifact.
interpretation,
Yeah.
it's an interpolation artifact. Yeah, and so if you use spline interpolations across here, it would not show up. It's because there are these sudden discontinuities in brightness.
Is this the MAC banding?
Is this the what?
MAC banding? If you have-
Mock banding.
Yeah, right.
It is mock banding. Yep. All right. So here, it's also ordered, low here to high. Is there more separation? I kind of feel like I can see more levels in the middle there, but I can't,
I can't see the triangles now.
Yep.
Okay. Rectangles.
All right. So the bivariate principles are if you have two different colors, you want to show kind of two different variables with color. You might imagine you could do three, right? Because we got three axes. We got red, green, blue. Well, that might not work. Well, we got hue, light, and saturation. We can at least do that. It turns out Penny Reingens did her dissertation here, studied that, and you can't get three. If you're lucky, you can get two, and kind of very careful with what you do. And so if you have a two-variable color map, so there's rows and columns, and there's diagonal. So rows and columns, I can tell the value on the row separately from the value on the column. And diagonal is kind of, there's this area in the middle where they're the same, and I can tell if it's above the diagonal or below the diagonal, right? Those are kind of two different questions you might be wanting to ask about your data. So here's a data set, kind of a 2D color map that has rows and columns and diagonal, right? So the diagonal is pretty straightforward. Is it green or is it purple, right? If it's gray, then it's kind of along the diagonal. Green is above, blue is below. And this is looking at hours of week you worked versus the highest grade level, right? So it's kind of give you an incentive to go to college, right? You already knew this, you're here, right? The second is a little bit more challenging, but you can say, is it green or white? And if it's either of those, then it's along the kind of rows. Is it purple or white? Then it's along the columns, right? And so you can answer that question, but it's not as easy as the diagonal question. But you can answer the question with this, okay?
What is this of?
This is a plot, what is this, what is this of? I don't know what this region is of.
What are we supposed to get from that? What's the good?
All right, so what you're supposed to get from this is you can tell from a given location whether you're on the diagonal or above the diagonal, which is green, or below the diagonal, which is blue.
Blue?
Sorry, purple.
Below the diagonal, okay.
And you can also answer the question, am I high in the hours of work axis? And the answer is if I'm white or green, then I am. And if I'm dark or purple, then I'm not. And am I high on the education axis? And if I'm purple or white, then I am. And if I'm green or black, then I'm not.
Okay.
And again, you're stretching to get two variables into a color map. And we can see that you're stretching here. Now here's an example where you don't have that behavior, right? So here's two different axes for the census data. And this is, you come here and you pick a color and you kind of try to find it over here. And there's no way you're going to know which axis you're on, how far you're up, are you above or below the diagonal. It's just whatever color they happen to pick for each of those squares, right? So, go ahead.
If you go back to the last time, suppose a point is at the bottom right.
Yep.
So what does that mean? It is like low on the hours?
So if it's bottom right here,
Yeah.
then it means that it's low on the hours of work and high on the education. Right, so you got your PhD, and then you went to work at McDonald's, but didn't work but a couple hours a week. Yep. And then, yeah, I should go find out what this is a map of, but yeah, all right. Okay, so now we're going to look at kind of hue versus saturation, right? And so along the bottom here is like my least favorite color map, because it includes the rainbow and saturation in one thing. So here is kind of unsaturated to saturated is the certainty. And so this is one, the one good thing if you have a data value that you can't tell what's going on, mapping it to uncertainty actually makes sense, right? So the one good thing to map the transparency is uncertainty, right? I can't tell what the data is. Good, because you shouldn't be able to tell what the data is. So here, certainty is mapped, kind of very certain is saturated, uncertain is unsaturated, and then hue is used to map the data set here, right? And so very challenging to get information about the display. So you don't have rows and columns, so maybe, yeah, so I guess there's no diagonal.
Actually, there are diagonals, but they're
But row
wrong.
versus column, you can probably do okay.
I mean, there are these artificial diagonals, and it's almost non-linear as you go
Right,
down.
this kind of thing happens.
Yeah.
Yep,
Like if you look through the yellows, like there's hardly any difference until you get to almost the very bottom, so
yep.
that's terrible.
All right, so it's, not separable, hue's not perceptually ordered, there's no diagonal, and yeah, okay. So, some univariate color scales, right? So here's some ways you might go about making a color map, and we're going to see kind of each of these, how they fit these principles, how well they work for what we're trying to do. So redundant, there's color model components, grayscale, hue, saturation. Redundant scales, where you map multiple of those channels to the same thing. And then, the question about do you want a double-ended scale is kind of like, do you have a ratio data set where there's an important above sea level, below sea level component. All right, so you can take just one of the color model components and vary it, right? So we've seen all these already as examples. There's the grayscale color map. There's a saturation scale where you basically take a saturated color and mix it with gray until it turns just white or gray in the middle. And then there's the spectrum, right? So at this point, you should be not letting a boo hiss. We should hear this coming from the crowd.
If you take the spectrum and normalize for luminance, do you get something different?
If you talk to Chris Healy, he thinks that you kind of do.
Because it seems like that would kind of solve that would make it.
But it turns out if you
No.
take the black body ratio spectrum, you do better, right? And so it turns out my statement, formal statement on the rainbow color map is not that it's the worst color map you could use, no. It's that there's always a better choice.
What if we use white instead of green in the spectrum, would be better?
White
Yeah,
instead
would
of
be.
green here.
That would be a lot
Yeah.
better.
It would emphasize differences between.
I see, so you're saying that would end up making being a double-ended scale. and it would go from white to blue, white to red. Yes, and so this is what they, kind of ended up as the compromise for peer review as the default color map. Indeed, it does have that benefit. It shows you high and lows. It gets you some idea of what you're seeing in the color channel, and it's not completely isoluminant. So yeah, that is a good idea.
In the para view, if you go into the edit color option,
Yep.
and then you have this to show the color in the form of components along X, Y, Z, so something similar.
So if you go into the color map editor in peer review, there's a whole bunch of presets, but you're saying you can set the individual colors along the road. That's correct.
X, Y, Z. So
X, Y, Z.
along the axis which you would want to model. Either you model the color depending upon the magnitude,
Okay.
X, Y, or Z. So
Huh.
it's there in the guide tutorial as well.
So you mean like if you're mapping a vector field,
Right.
yes, and you can color according to the magnitude of a vector field,
Yeah.
or the X or the Y or Z, right? So that turns out to be independent of the color map.
But
Right.
they use the same component model for that.
So you're saying that they use like this to show X, and this to show Y, and this to show Z?
I'm not able to discern depending upon the color they're using, but they use the thing component scale.
Yeah, so we're gonna have, well, you're saying the component scale is the name that they use it, right? Okay, so I think what they mean there is vector component, X, Y, or Z, not kind of component of the color space.
Okay.
Yeah. All right, so if we take the first one, the grayscale color map, so this is looking at, basically, this is a slide I got from Penny Reingens, and so this is, something, that I was using in the visualization class. Then when Colin was redoing the next edition of his book, he had sent me a draft of it and said, hey, you should look at these things from Penny Reingens. He ended up putting them into the book, and so her work ended up being a good way to think about these scales, particularly because it's got the same kind of data with multiple color maps, right? So we can see side by side how these behave. So this is kind of a grayscale color map, and so this is looking at the ozone, kind of in the northern hemisphere, the southern hemisphere, down to the poles, right? And so we're trying to understand kind of what is the shape and distribution of this total ozone, right? So there's 177 to 438 parts per million, perhaps.
So it looks like there's some sort of diagonal lines cutting through.
Yeah, there's a very interesting artifact going here.
It's a satellite in polar orbit.
It's a satellite in polar orbit, and we're seeing stripes. Good.
Those could be the mark types.
They could be mock bands if there were triangle tessellations along the data that way, but I think in fact they are kind of the satellite stripes as it goes around and around.
It's telling because they're diagonal and not, yeah.
Uh-huh.
Yeah.
But mock banding could produce a similar effect, although we're getting really a strong edge effect here, not just an interpolation. All right. All right. So this is a saturation scale, and so here, excuse me, there's kind of a white area, a red area, and a sudden change in the middle, and some of that has to do with this particular projector and the gamma correction that we're doing. You could kind of stretch that out a bit. But we expect that as you have less luminance change, we're going to see less detail, and so that's going to be a trade-off that we're going to have. And so this is kind of showing the same thing with the saturation scale. This is the hue scale, right? The same data drawn again with the hue scale. And here we at least only have red at one end, and it happens to be the low end, okay? Because that's the alpha, kind of Roy G bit goes this way. You might think that this is kind of blue to red should be a hot one and goes the other way. Either one is okay. All right, so that's just kind of independent color scales. Then you can also take two or more of these components and vary them together to try to kind of emphasize and see more separation in the display. So we're going to see hue with luminance and the black body radiation scale. So here basically the same, you're using kind of two techniques to show the same data because you really want to see that data better, right? And in fact, we're going to see some design examples in class where you might put all the different kind of techniques you can into the same data set because you really want to understand that data set, and that was the only one that was there, right? So you might do height fields plus contours plus a color map all on the same data set because you only had one and you wanted to see what's going on. So this is within color trying to do that. All right, so this is basically hue plus luminance. Unfortunately, blue doesn't participate in luminance, so you can kind of crank it up as blue as you like, and it's not going to help with that. So in this case, there's a little bit of a dip in the luminance, but at least, ignoring that, you get kind of a brighter and brighter and brighter thing. It's going around in color space. There's, 1, 2, 3, 4, 5, 6 in different ranges you can see. So this is perception ordered to a computer, but not to a person. So this is basically hue plus luminance in a different order. And so here it does get brighter and brighter and brighter. And now we can see different regions, the blue region, the black region, the green region, the white region. And we can see kind of more details because there's luminance contrast around that than we could see in the hue alone. So this is starting to look quite optimistic. And this is the kind of similar to the black body radiation spectrum. So what do I mean by that? So if you take a black body, a cannonball, and you heat it up in the fire, right? It first gets red hot, and then it gets yellow hot, and then it gets white hot, right? So this is the same thing as color temperature in photography, but you're just always in the white, zone, right? And so this is the black body radiation spectrum. This is perceptually ordered, I guess not because we're necessarily used to watching cannonballs heat up, but because you can tell brighter means more, darker means less. It's got something that the grayscale color map doesn't, in that it kind of wanders around color space, right? So it starts, goes up to the red, and then to the yellow, and then to the white, and so you got 3 different zones. And so there's some contrast effects that get removed, and so you can tell, kind of, for example, that this spot here is brighter than this spot here because it's white instead of just being yellow. But you still get the high details that we saw from the black body. Sorry, from the grayscale. All right. So here's kind of all of those together, and so the question is, when we look at these, which of them show kind of fine detail best?
What kind of detail are you interested in finding? What question are you asking of pictures?
Yeah, so if there's detailed, there's small features in the data, I want to see them.
The small changes?
No large changes over small areas.
I would say the bottom right 2.
These two have pretty good detail shade, yep, compared to this, especially in this region here. Right, you're going to see the details here, yep.
Actually, they pop a lot in the lower left as well. Those ones on the top particularly.
So some transitions pop, right? So this particular transition pops, but the detail there goes away, right? And so it kind of flattens out and you see a boundary.
Interestingly, you see sort of 2 or 3 levels on the lower band there. You sort of have the magenta and the blue and then the sort of light blue.
Yep.
Over there, they kind of blend, on the right, they blend together. It's just sort of a...
So you're skipping ahead to my second question,
It's
which ones show you whether the ozone is higher in the northern band than in the southern band, right? And as you say, you can see very clearly that this comes all the way down here, but it doesn't ever get up to red except subtly a little bit there, right? You can see that a little bit here, some here, not really here, right? And so if you ask kind of how, is this spot brighter or this spot brighter, a little more challenging to tell than in this image, right? So this one kind of has both the kind of fine details and the ability to tell kind of which is the kind of overall largest area. This one does this as well, although it's losing a little bit of details down in here.
Is there a name for that bottom middle color map?
I don't have a name for that bottom middle color map, yeah. So there's kind of the kindred to this, we're going to see in the next lecture, are that you take red first and then green and then blue, or blue first and then green and then red, or different orders. And this may be, except it's not quite, blue first and then green and then red, right? So it kind of is something and then blue first and then green and then red. And so it's kind of a different ordering.
Do you sometimes get interesting things if you take the same coloring and show it inverted next to itself? I know with X-rays that can often be quite useful, but
So you would like look back and
you show
forth?
the negative.
Uh-huh.
Yeah. Often you can see things in the negative that were not visible in the.
Yep, and we saw that example earlier with kind of going from this map to this
Yeah.
map. Yep.
Are those the same? Those are the same. It's just inverted.
It's the
Really?
same, just
Yeah.
inverted. Yep. And in this case, on a projector, I get to see a little bit more kind of details up in this area than with the other one. All right. And so far we got, these guys are pretty good at both the questions we've asked of them. This guy not so good at one, but good at another one. This guy not so good at one, but better at the other. All right. And so which ones of these are perceptually ordered? Right, so you don't have to know the magic incantation to figure out the ordering of these. This one? Yep, this one? Yep.
Possibly.
And then we can argue about this one.
Right.
Yeah. Uh-huh. Yeah,
It's not immediately obvious.
all right.
It's only because it's a vaguely red color at the very end. I conclude that that's the lowest, but you could also argue that it's the highest, right?
All right. So, double-ended scales. Let's say you care about height above sea level, bank balance being negative or positive, and so forth. So basically, one way to do this is to take two distinct scales and you join them in a neutral middle, right? So you can use two saturation scales or so forth. So this basically segments into two groups, and you can see the extremes in the data range. And so here's a double-ended income scale. It looks very much like the one we saw that showed kind of water versus land. It goes to blue at one end with increased saturation. It goes to brown with increased saturation at the other end. So more intense hues stand out, and they draw your eye to outliers, right?
That one has a weird property that it really creates a huge distinction between the third and fourth categories. Those two, like the orange stands out, that light orange, and then so it's kind of lying to you. So you see these little clusters in like that big, what county is that? I don't remember what county that is, but there's a couple of areas that really,
There's two things
they're
that,
kind of in the middle, but they sort of blend into the rest and you don't notice them.
yep.
So it's kind of lying to you a little bit.
It's emphasizing something that you think it may not be intentionally emphasizing.
Right.
That's what you mean by
Yeah.
that. That's right. So indeed, not all of these have the same separation. It turns out that on a given projector with a given camera, different ones will have that characteristic. So, my wife is a photographer, and she says, I just want the people to see it on their screen the same as I took the picture. I'm like, okay, but if they change the brightness of the monitor, it's going to be different. She says, yeah, I understand that, but I just want it to be the same when they see it on my monitor. And so one thing you have to get used to, and what Patrick was talking about before, is physicians, they have to use calibrated monitors in rooms with a known amount of light in them before they're allowed to read the x-rays, because indeed it shifts where these things are depending on the color temperature, the bulb, the brightness of the room, and so forth. So give them a little bit of credit there, but yeah, at least this is a double-ended income scheme.
Are there tricks to be immune to that? Or
Yeah,
essentially?
you can run a color calibrator and stick it on your monitor, and
If you're giving a presentation on an unknown projector, are there
yep, on the
tricks you
Mac.
can play?
On the
to-
Mac, you can actually run this color. It's a brightness calibrator at least. And
I'm saying, can you pick colors or all these different variables such that it's substantially immune to these differences in the
No.
gamuts of projectors?
Well, yeah, you can use black and white.
Yeah.
So if you just go to jam it to the edge of the ranges, but there's no way to deal with that. Yeah. So the closest you can get is on the Mac. There's an app that when you run it, it kind of lets you calibrate the go until these things look the same brightness. Go until
Yeah,
you see this
Windows
pattern
has that
here,
too.
and it basically is you calibrating the monitor, right?
Windows has that
Yep. So Windows is catching up. Excellent.
too. Had for a while.
All right, so the other thing besides these to consider when you're looking at color is, are there interesting values in the data, right? So this is a question for the scientist. Do you care about the tree line, right, in this? Do you care about a particular value being, what happens? If so, put some striking color at that range, right? So the good news is if you have a banded map, you can just put the band right where it does matter, so you can see that striking difference where it's important to the scientist. Use a double-ended scale if there's a 0 in the range. If there's high spatial frequency, right, so this is jargon. What this really means is there's small features and you care about seeing them, right? So just to go a little bit off topic, so this is, a low spatial frequency. This is a higher spatial frequency. This is a very high spatial frequency, right? And so this is basically a sine wave, and the frequency in space goes up and down. If you do the Fourier transform, which is very popular in filter, in image analysis, this is the way you think about the image. You convert it into a bunch of spatial frequencies, and you say if it's got high spatial frequencies, then you care about this. But what this really means is, in your data, are there sudden changes that are small, and did the scientists care about that? If they did, then you need to use luminance change, because that's how we see small detailing features. All right. If you're going to have potential color deficient viewers, you don't want to depend on the red-green differentiation, right? So it used to be, when I was growing up, stoplights always were vertical, and the green light always had a little bit of blue in it, right? And so if you were red-green colorblind, didn't matter, because you knew the green was on the bottom, the red was on the top, and they were a little bit different color blue anyway. You drive in cities nowadays, and they sometimes turn them sideways, right? There may be a convention for which way they turn them. I'm not sure that there is. In any case, I don't know the convention the first time I see one. And they use LEDs, right, which have a very fine line of brightness, and so it's perfect green, perfect red. So expect more accidents from 10% of the men as they drive into the city for the first time, and we don't have that convention, all right? So is there a convention in your application area, right? So don't make your carbon atoms something other than black. Don't make them pink just because you like that. It'll confuse a scientist. Unless there's a strong reason to make them pink, like you had to draw attention to them, and then you better explain to them what's going on. If there's associated colors with variables, use the associated color, right? If it's kind of, if it's temperature, high temperature, red would be a kind of way to think about this. And again, red for hot, red for bad in the US.
So I'd argue that if you were showing like meteorological data where they often use that rainbow scale just because they've been using it for 1,000 years,
Yep.
you might choose to use it even though there's always something better than that.
I would.
Because they're used to seeing it. You wouldn't?
I wouldn't, because it makes me crazy. I would explain to the viewers, yes, we're not using the rainbow color scale because it's bad. And so if you watch any of the, I'm turning to a marketing campaign, right? Ours is perceptually better than all the other techniques out there, and here's why. Yeah. In fact, meteorology is one area that I keep thinking about, and that should probably be one of the class projects.
You should,
because if you changed it, it would like change the world.
When we were having all that tornado nonsense a couple of weeks ago, we were actually watching Weather Channel or something, for way too long, and it was driving me nuts. Like I kept trying to look for a legend. Like, is that high or low? Is that color worse or
Now you know the internship you want.
But I suspect that they get used to it enough that their brains map it properly. And you might actually screw them up if you were to. You might actually screw them up if you were to change color palettes.
You would certainly
interesting.
make them think. Yeah. All right. So size and background effects. If you want to if you want to see a very small patch, you need to make a very saturated color, or you're not going to be able to see it. Larger patches you can see more easily, especially it's a hot problem in the blue, yellow direction. And saturation size illusion, right? So
Yeah.
a bunch of illusions. So something that's saturated looks bigger than something that's unsaturated, even though it isn't. And so if you want to trick your audience, there's a way to do it. But if you don't want to trick your audience, be careful not to increase the saturation when you didn't need to. And so one of the things, when you're looking at that set of counties, is some of them look bigger because they were more saturated than they did. If size is not your primary concern, but just laying things out, then that would be okay. There's a chromatic contrast, right? So just as we had luminance contrast, where kind of backgrounds made things seem brighter if they were darker, you have chromatic contrast, and so those two X's in those things are the same color. But to me, from here, the one on the left looks blue, and the one on the right looks red because their surrounding, are the opposite of that. So this is basically why when you watch a television, you don't notice that there's anything weird going on. But if you go to the television store, you see, wow, these are all different color televisions. What's going on with that, right? Because you can see them side by side, and if you don't have them side by side, it all just averages out, and you see everything fine.
Well, even if you have a television that's all whacked out, if you watch it for a while, it starts looking normal.
Yeah.
It's
You auto white balance.
exactly.
All right. Brown. See, I told you brown was coming. So it's dark yellow, but not when it's alone in a dark room. So it has to be surrounded by brighter patches. So it won't be seen as belonging to the family of yellows, which is a little annoying because you want to have kind of a yellow to black color map, and then there's this weird color shows up brown, and it's not seen by the user as yellow. And Winston Churchill feels really sorry for brown around all the colors. It's kind of like yucky color. All right. Other places to go. Color Brewer is a good place to build yourself a color map for characteristics that you care about. You can take the colors from that, stick them into the peer review editor, and get whatever color map you wanted to do for your homeworks or for your final project. There's a color FAQ online, and then Penny Ryan's color perception and apps that she maintains there. All right, and so next Tuesday, we're going to take this color knowledge plus some luminance knowledge plus some other things, and look at all the different ways you can display 2D scalar fields. And kind of which are better for what things. And the good news is there's choices there that can do some things that color can't even do.